Good afternoon to you all. Welcome to the sixth lesson, satellite communication, which is the second last. Today we're going to look at the propagation of signals in space, how they are affected, and what form of orientation should they take. My cell number is this one, which you use for the group. If I'm using UJ, this is my office number. Okay, without further waste of time, let's look at the work. As far as chapter 4 of your note is concerned, it's giving you an introduction onto atmospheric losses. Remember, the atmosphere is the first layer which you encounter on the sky, so directly above us. And we look at the effect of the ionospheric layer, which is above the atmosphere. What's meant by attenuation and other forms of impingement on the propagation of signals. Chapter 5, we won't do much here. It's giving you types of polarization, which is the orientation of a signal, the direction of an electrical signal of a wave with respect to the magnetic component. Well, in most of satellite equipment, you may come across right-hand circular polarization and left-hand circular polarization. So it's spinning, and as it goes. It's not limited to that polarization. We have vertical polarization, which we've seen in antennas. Sometimes you call an antenna vertical polarized in radio. It can be horizontally polarized as well. So this is your food for thought. Go and look at forms of polarization and be able to describe each. Refer to your notes, which you have here. Now, what are the atmospheric losses, which is a layer above us? Well, it makes sense to say these are weather related, and they are called atmospheric attenuation. Well, you might find yourself in a plane right above there in the sky, and you don't see any rain. It's raining somewhere below you, right there, and the moment you land, you see that it rains. So at the lower level layers, that's where you're gonna find weather related issues there. So, well, it's simple called absorption losses. No, absorption losses are simple called atmospheric absorption. That's how it's named. Now, there are two major kind of absorption, which are classified according to the frequency. The first one occurs at 22.3 gigahertz, such a high frequency. That it's due to resonance. For sure, you remember resonance is done in electrical engineering technology, RLC circuit. Got other parallel series resonance, but then it's a component of frequency which tend to give you magnified current or magnified voltage. So here in this instance, a component of frequency where the losses will be severe. So if this is a gain, Bessel's frequency curve, There's your frequency. Doesn't want me to draw to put F. Disappear. There's your frequency, and there's your gain. Now you'll find that as this thing, what is this thing trying to achieve? There's your gain, and then as your frequency progress, and then you reach 22 over there, and then out of the blue, and then your signal drop, and then it rises again. So it goes till you come to the next one, 60 gigahertz. At 60 again it drops, and then from there. So this attenuation here is caused by at a certain frequency, where in the first one is a case of resonance absorption and by water, that is at 22, and then from there you got another one at 60 with still another resonance at 60 gigahertz by oxygen, right? So, well, in this case of resonance, it results onto a loss. So if you remember in resonance, in another thing, you happen to have a lower resistance in a coil. So that is here, you have a low output because of magnified attenuation. Now, there is another loss which occur above the atmosphere. In here they're showing you the layers. You see that they're showing you a troposphere, and then there, somewhere there below, you should have your atmosphere, and you have your ionosphere. Now in here, it's an explanation for the ionosphere is given. Is the upper region of the Earth, so this is the Earth, atmosphere, so it's above the atmosphere, confirmed, which has been ionized mainly by solar radiation. What is meant by being ionized? If you've got an atom, and then you have valence electrons, outermost electrons, this thing is not friendly to me. There's your atom. You've got a nucleus right there, which is positively charged. Got electrons, so outermost electrons. And these atoms lose an electron. Once it loses an electron, it becomes a positive ion. And another atom there takes that electron which doesn't belong to it. It has got more electrons now, and that becomes a negative ion. This one becomes a positive ion. So now this is an ionization effect where there is a loss of electron. So the solar radiation tend to create losses and gain of electrons. Remember, for an electron to move, it needs energy, and solar is another form of energy. So that layer, it's ionized. Now, to sum up the propagation impairment, we've got this table 4.1. Now, here is a kind of impairment which you must be able to remember, and what is it that is associated with, and the cause, and well, they say importance, not necessarily important here. It's about the effect. Now, attenuation sky noise, it's due to atmospheric gases. It affects, there's got an impact on frequencies above 10 gigahertz. Signal depolarization is caused by rain. Where do you think this thing will happen? If it's rain, it should be in the atmosphere, right? So that affects C and Ku bands. Refraction, atmospheric multipath, it's caused by gases, and it affects communication where the tracking is at lower elevation angles. Okay, so the list on and go. So what you need to know is, you should know what impact the Ku band. You should see the greater impact is on signal depolarization. If we look at C band alone, inter-system interference. So be able to understand that table. Rain attenuation is a function of rain rate. Rate is the how much is given per unit time. So if you've got more water within a short space of time coming from rain, it means then the rate is high. Okay, now we'll look at example 4.1. Propagation impairments can be caused by may to impacted less by hail, ice, and snow, because they've got less water content, and ice can cause depolarization. We'll talk about the vertical and horizontal polarized. Look at what depolarization is in chapter 5, and look at this reference as well. Okay, in your problem, that table which we described. So we look at the impairment, and then from there, and what effect, what does it impact? So associate each component there in the table with the correct part. So see that you can answer these problems as far as this section is concerned, and go through the work which I advise you to look at, which is polarization as it's discussed in chapter 5. With that, folks, we come to the end of your lesson for today. Make sure you visit this, because test 3 is on its way. We only have one class left. We'll mark all your material and finalize your work. And enjoy the rest of the day. And goodbye.